Welcome to this central force problem. Today we are going to discuss the Kepler problem, or specific applications of the uh, theory presented so far to astronomical problems. The force is given by the familiar inverse square law of the radius, and the corresponding potential is just minus k over r, where k is the constant specific to the problem we are discussing. And we already know from equation 339 that up to some integration constant theta prime, uh, the polar angle is given by the following integral. And the expression here can be solved exactly through the following observation. So what we have under the square root is a general quadratic form, uh, where I've replaced the u variable with an x, and this one will have the discriminant given here. And as such, we know that the roots of the expression here have these values, and as such, the quadratic form can be factorized in the way given here through the two roots. And if we work this expression out, another closed form should be the one given here. Then, if we take the square root of the quantity here, and we label it by some variable t, which is just an integration variable, it's not a time, then we can transform the integral for our angle to the form here. And this one has a straightforward solution in the form of the r cosine function. And then all we have to do is replace the general constants involved here with the quantities specific to our problem. So these are the values of alpha, beta, and gamma, and the corresponding value of the discriminant. Then by using equation 350 and 353 together, we can find the angle as theta prime, the integration constant, minus the r cosine here. And then the last thing we have to do is to remember that u is equal with 1 over r, and bringing this into the previous result returns the orbit equation, where the radius is given as a function of the angle theta, and the integration constants, the constants of motion, energy, and angular momentum. So it's important to notice that theta prime can now be identified with one of the turning angles of the orbit. And furthermore, it is important to notice that only 3 of the 4 constants of integration appear in the orbit equation, which is a general characteristic of orbital motion. This is due to the fact that the 4th constant would be fixing the initial position of the particle, which is irrelevant as far as the orbit equation itself is concerned. The initial angle theta 0 would be required in the integration of the conservation law for angular momentum, and would thus complete the solution with the radius and the angle given as functions of time. In any case, a conic section of eccentricity e and having a focus at the origin is given by the expression here, where c is just some constant. And thus, when comparing this with our own result, it is clear that the orbits in the Kepler problem are always conics of eccentricity e, having the expression here, a square root involving the conserved quantities of the motion and the constants of the interaction, so the mass and the force constant. And their general classification would be as follows for the conic sections involved in the Kepler problem. If the eccentricity is greater than 1, then the energy is positive, and the curve that is traced is by the particle is a hyperbola. If the eccentricity is equal with 1, then the total energy is 0 when the orbit traced is a parabola. If the eccentricity is smaller than 1, then the energy is negative and the orbit is an ellipse. And in the case where the eccentricity is identically 0, then the energy has the expression here and the orbit is a circle. Now, in the particular case of circular orbits, uh, neither the kinetic nor the potential energy change in time. Uh, they are both constant, and the virial theorem states that since E is equal with the sum of kinetic and potential energy, and we know that T is constant and equal with minus V over 2, we get that the total energy is V over 2. And since V is given by the expression here, and we are discussing the circular motion, then the energy is simply minus k over 2 times r0, where r0 is the radius of the circle. Now, if we plug in the result 341 in this expression, we can find the radius of the circle as a function of the angular momentum. And then if we use these two together, we prove once again that the energy has exactly the expression we had found previously when we had derived the general equation for the orbit. As an interesting application, we can consider the situation where we have motion on a parabolic orbit having the same value of the angular momentum as on a circular orbit. Then for the perihelion distance of the parabola, we can write the identity here, which follows from energy conservation, and then we can immediately extract the perihelion radius as the quantity here. We can do the exact same thing for the motion on a circle of radius r0 and find the expression here. And now it's very clear that since the L values are the same in both cases, uh, for this particular configuration, um, the perihelion radius of the parabola is half of the radius of the corresponding circle. Now, in the same conditions, we can find a similar result for the velocity at any point on the parabola. So once again, we can write the energy conservation for the motion on the circle, and keep in mind that there's a squared factor missing here, so this is r squared. And also keep in mind that on a circle, there is no shift in the radial distance, so the magnitude of the velocity is given just by the ratio between L and the product m times r, where r is the radius of the circle. So from these two, we can find the velocity for motion on the circle as given here. And then if we write the energy conservation for the motion on the parabola, we can extract the corresponding velocity as given here. And once again, comparing these two expressions, it follows that the velocity on the parabola in this particular configuration is just square root multiplying the square root of 2 multiplying the velocity on the circle. In the case of elliptical orbits, energy conservation at the turning points is stated um, as given here, and so essentially I've written the energy conservation for the case of uh, vanishing radial motion, vanishing radial velocity. So this will determine the apsidal distances as the roots of the quadratic form here, and then the semi-major axis is automatically determined by this expression. So it's simply minus k divided by 2 times the total energy, and the fact that the semi-major axis in a inverse square problem, inverse square of the distance problem, um, depends only on the total energy was something of considerable importance in the development of early atomic models, and particularly the Bohr model for the hydrogen atom. Furthermore, if the semi-major axis happens to be uh, R0, then the energy is just minus k over 2r0. So in this specific situation where the these roots are the same, we just are equal, we just recover the expression for circular motion. Now, using the result here, we can rewrite the eccentricity for the case of elliptical motion as given here, and we can solve this equation for L squared over mk in order to obtain this result. And now if we plug equation 355 in here, we can recover uh, the orbit equation in a slightly different form, uh, which allows us to make the following two observations, namely that the upsides will occur when theta minus theta prime is equal to 0, which just gives a radius equal with a multiplying 1 minus c, which would be the perihelion. And if theta minus theta prime is equal with pi, we will get a radius equal with a multiplying 1 plus c, which is just the aphelion. And these are the results expected for an ellipse. Now, the velocity on the ellipse can be resolved into components, namely the radial and angular velocity. And the radial velocity is simply the radial momentum divided by the mass, and the angular velocity is the angular momentum divided by the product between the mass and radius. And then if we write the orbit equation and we take its derivative with respect to time, we find the result here, and it can be recast in this form with the help of this constant v0, which is just L divided by m multiplying a, the semi-major axis. And what's important to observe here is that this derivative will vanish at the upsides. So when this sign is 0, but at the same time, so this derivative corresponds to the radial velocity, but at the same time, the angular velocity will attain its maximum at perihelion and minimum at aphelion, given this expression here, because at perihelion, so this will be minimum and the overall quantity has its maximum, and the other way around at aphelion. And just as some illustrations, here we have an example of various conic sections, so a circle for zero eccentricity and more and more eccentric ellipses as this parameter increases. And also notice that I've chosen the parameters in such a way that for this particular figure, the perihelion does not correspond to theta equals 0, but rather to theta equals to pi. So doing things the other way around, we just flip the reflect the figure along the y-axis. And this is a plot of the normalized radius vector to the semi-major axis as a function of the eccentricity, and we observe two linear trends, an increasing one for the aphelion distance and a decreasing one for perihelion. And this figure shows the normalized radial velocities as functions of the normalized radii, again for various values of the eccentricities. So the points where the normalized radial velocity vanishes will correspond to the two apsidal distances. And Finally, a plot of the normalized angular velocity as a function of theta. And once again, it's given for the configuration illustrated here. So the maximum follows at a perihelion distance, so at theta equals with pi, and the minimum at aphelion. And it's important to notice this because it is entirely consistent with with Kepler's second law of planetary motion. So the observation that the radius vector of a planet will sweep equal areas in equal times. It is something that we will touch again upon when we discuss the motion in time in the Kepler problem. Still on the topic of elliptical motion, we will now consider an elliptical orbit and name the distance between the two foci of the ellipse by the name of equant, and we will denote this with q. And we will assume the particular case of a small eccentricity of the orbit, and we will try to discuss the motion as viewed from the empty focus. So with this definition of the equant, q is simply going to be given by the product here, 2 times the eccentricity times the semi-major axis. And now we want to write the radius using the law of sines. So essentially, this is the radius as measured from the focus where the center of force is, and it is given by this expression where q is the distance from the origin to the empty focus, and then alpha is going to be the angle swept by the radius vector measured from the empty focus. Theta is going to be the normal polar angle as seen from the origin, and beta is the angle which completes the triangle formed by these three angles, alpha, theta, and beta. So this, if you make a quick drawing, this you'd have a situation like this. Like, so this here's the origin. Our particle is somewhere here, and this is going to be the radius vector. This is the angle theta, and then if the empty focus is over here, then this is going to be the angle alpha. This is what is beta, and the distance over here is the equant q. Right. So if we write the radius this way using the law of sines, then we can immediately switch things around like here, so we can get sine of alpha divided by the radius is equal to the quantity here is just the sinus of the angle beta over the equant. And then if we divide everything by cosine of alpha, we can write the result here. So the tangent of alpha divided by r if it's equal with the difference here, which is just, well, obviously the sinus here is of theta minus alpha. We expand it using the simple trigonometric identity of the sine of such a difference as a difference of products between sines and cosines. So we get the result here, and this allows us to write the tangent of alpha, so the tangent of the angle corresponding to the motion viewed from the empty focus as the ratio here. So it involves the angle measured from the origin and the ratio between the equant and the particle's radius. And now we need to bring several things together. So first of all, if we write the general orbit equation and take into account that E is assumed to be small, Then we can write this approximate expression for r, which follows immediately by solving this for r and using a Taylor expansion for the small denominator here. So we have this result. Then by using the same method, we can approximate cosine of theta plus q over r to the denominator here to give this expression. And knowing tangent of alpha, we can also calculate 1 plus the square tangent and approximate it with the form here. And we need all these things together with the time derivative of equation 1, because we ultimately we want to see how the motion looks when viewed from the empty focus. And if we do all these calculations, we get to the result here. This is still in intermediate form, so I haven't yet I haven't replaced the sum here by this result, but getting to the expression here and working everything out, we can ultimately write the time derivative of alpha as being equal with the time derivative of theta times this difference. And we know the time derivative of theta from the conservation of angular momentum. So then what follows immediately by plugging this back here is that the time derivative of alpha is given by this product. And since the product here is just 1 minus q over a times cosine squared, and since this involves an e squared, we can neglect it. So we end up with the time derivative of alpha being a constant. It's just the angular momentum divided by the mass and the square of the semi-major axis. So the conclusion is that if the equant is taken as the distance between the two foci of the correct elliptical orbit, then the angular motion is described accurately to first order in the eccentricity by the Ptolemaic picture. And as viewed from the Earth, the Sun rotates uniformly, which constitutes the basis of what was the ancient Ptolemaic model of the solar system. We are now going to consider some examples of some simple examples of scattering in elliptical orbits. For the first instance, assume that at the perihelion of an elliptic gravitational orbit, a particle experiences an impulse s in the radial direction and is sent on another elliptic orbit. We are to determine the new semi-major axis eccentricity and orientation in terms of the old ones. First of all, let's see what happens with the magnitude of the angular momentum. So the new angular momentum is going to be given by using its definition by the radius, which is in this case the perihelion radius of the ellipse, times the magnitude of the linear momentum, which is going to be the square root of the squared linear momentum at perihelion prior to the impulse plus the square of the impulse itself, and of course the sign between the two, and the sign of the angle between these two vectors. And this is simply going to be the original linear momentum divided by the same square root. So these two factors simplify, and as such the the results should be obvious from the very beginning. The orbital angular momentum is unaffected by such a collision, since the impact is parallel with the radial vector. Then if we look at the new energy, so the new energy prime is just going to be equal to the old energy plus the contribution of this impulse, which is just an s squared divided by 2 times m, where m is the mass of the moving particle. And then knowing the the definition of the value of the semi-major axis of the new orbit, we can immediately calculate the semi-major axis in terms of the old one as the quantity here. Furthermore, we also know that the expression of the new eccentricity in terms of the angular momentum and the semi-major axis, so we can immediately write it in terms of the old one as follows from here. And in order to find the orientation, we just need to write the orbit equation for the perihelion in the two instances. So this is the old equation, and then this is the new one in terms of the new eccentricity and some angle phi, which is due to the uh, due to the scattering. And we from these two, it follows immediately that the cosine of phi is just the ratio of the old to the new eccentricities. As another example, assume now that a planet of mass capital M is in an orbit of eccentricity E being equal with 1 minus alpha, where alpha is some small quantity, and this motion takes place about the Sun, whose own motion can in turn be neglected. Now, when we are at aphelion, the planet is struck by a comet of mass M, where M is assumed to be much, much smaller than capital M, and the comet is traveling tangentially. In the case of a completely inelastic collision, the question we have to answer is the following. What is the minimum kinetic energy of the comet that would change the planet's orbit to a parabola? Now, first of all, from this set of identities, we can recover the result which we already know, namely that the energy for an elliptical orbit has the expression here. So this would follow just from the aphelion distance in terms of the semi-major axis and eccentricity, from the value of the energy at aphelion, and from the formula connecting the eccentricity, the angular momentum, and the semi-major axis for elliptical motion. So they lead us to the result here, which is already known. Then if we apply the conservation of linear momentum, we have the following situation. The momentum prior to collision was just the linear momentum of the planet plus the uh, linear momentum of the comet has to be equal with the linear momentum post-collision, which is given by, since the collision is completely inelastic, we have a new body having a mass equal to the sum of the previous masses and a total velocity v prime. And using the fact that the mass of the comet is much smaller than the mass of the planet, we can approximate v prime from this equality through by the result here. Then we need to look at what happens with the energy. The energy post collision, immediately post collision, is given here. So it's the kinetic energy of the new body minus the plus the potential energy at aphelion. And if we use the result 2 and expand, it follows that the new energy is approximately equal with the old value plus the quantity here. So the mass of the comet times the initial times, let's see who is v. So times the initial velocity of the planet and times the velocity of the comet. And then if we wanted this energy to correspond to a parabolic motion, so this quantity has to be equal to 0. And then from this we can then solve for the velocity of the comet to obtain the expression here. And then it follows immediately that the kinetic energy of the comet is just the square of this quantity divided by 2 times the mass of the comet. Then we also use equation 1, which will tell us the value of E, and we will use the fact that at aphelion the the motion of the planet is strictly angular. There is no change in the radius at aphelion, and putting these things together, it follows that the minimum kinetic energy of the comet has the expression given here in terms of the known constants provided by the problem. In summary, we have solved Kepler's problem and classified all of the possible orbits as conic sections of given eccentricities having the center of force located within a focus. We studied in detail the properties of bound motion, specifically the circular, elliptic, and limited case of parabolic motion. We have also treated basic scattering problems for elliptic motion. In the following, we will discuss the motion in time in the Kepler problem. So, with that being said, I want to thank you very much for watching the video. I hope it was worth your time, and I will catch you later. Goodbye.